So this is the CISSP. And we are, yeah, my thing is slow but not impossible. Okay, so we're down here on March 28th. So if anybody has their presentation ready, you can give your 4-minute presentation tonight and get extra credit. One student sent in a video and got extra credit. If you aren't ready, then next week is the normal time to do it, where I'm not going to have any lecture at all, so I'll have the whole class period for people to give their presentations, because there should be a lot of them. And I just plan to talk about some of the cryptography stuff in this chapter today for a lecture, and then I'll pause and let anybody that wants to give an early presentation. So, you're going to get to my slides. All right, here we are. Oh, good, okay. All right. So, Mick, I'll put Mick Sands on the list. And by the way, you should tell me whether you want it recorded and put on my page or not. Mick Sands. All right. Good. Anyway, good. And Hadik is also ready. Okay. I'll just make a note. All right. So, let me get my slides up here. All right. And looks pretty good. Okay, so, all right. So here are some vulnerabilities that can leak data out. Good, okay. One issue that came out was the Tempest project, the U.S. military project. This was mainly back in the days of CRT, vacuum tube, or CRT cathode ray tube displays, but they showed that computers leak out radio signals as the electronics sends things out, and you can pick up those radio signals and you can deduce things like what's on the screen and what people are typing. So if you want to be safe, you have to block these emanations, and pretty much what you have to do is be in a basement room with no windows, with metal in all the walls and floors and ceiling around you, so that it stops the radio. And in general, this is the issue of covert channels. Covert channels are where data is being transmitted in some way that you do not control. There is some path that is not passing through your security barriers. And so that those radio emanations are one. There are storage channels where you're somehow able to watch some storage location and deduce what's happening. And there's timing channels where you can measure the time it takes to do something and deduce something from that. Many, many ways to use this. One that UC Berkeley came up with about 10 years ago is you can just send pings to somebody's laptop or cell phone and get a reply, and you can time that, and you can determine their geographical location by just how many miles of cable are between you and them. And then there are backdoors, secret ways to communicate, that bypass security checks. The most common type is put in by the manufacturer. This is something Cisco's done about 8 times and had it exposed, and they had to fix it in the last couple of years, where there's a secret hard-coded backdoor password to get into the stuff. It used to be a common practice for the developers and help desk to get in there, but it's highly insecure because after it leaks out, then everybody can get in everybody's stuff. And then, of course, malware, where you infected your device with some malware that lets an attacker have remote control. And if you are now, the usual kind of malware exploits known defects, and if you keep your stuff updated and your antivirus and everything updated, that blocks it. But if there are zero-day exploits, which do something which is not known to the manufacturer or to any antivirus vendors, so even if your stuff is updated, it won't stop the zero-day attacks, and those are, of course, the most valuable and most powerful ones. Viruses are codes attached to an executable file, or these days things like macro viruses in a Microsoft Office document, and there's many types of viruses, constantly new ones, that infect machines and often spread. Worms, Trojans, and rootkits are things that typically do not spread, but they take over one machine, so a worm is something you send over a social network like a link, and Trojans lie about what they do, and rootkits infect your machine at a very low level, so that your machine is compromised fundamentally, and it's very hard to detect and very hard to remove. I see several more people ready for presentations. That's good. All right, so packers are a type of malware that contain more malware inside them in a compressed or obfuscated way. So when the packer runs, it unpacks it and it loads that more malware. And most malware is multi-staged, where you have a small thing to start and it loads more and that loads more. UPX is a common open source packer. Logic bombs are code that waits for some kind of trigger condition and then does something bad. They are often not malware that's detected or malware that spreads. They're often something put in by people like disgruntled administrators at your company. There was a famous logic bomb during the financial crisis on Fannie Mae and Freddie Mac to destroy the data of the major, lending companies for mortgages in America, and somehow they found it before it went off, which is pretty heroic. I really don't know how you would catch a logic bomb. So antivirus software is primarily signature-based. It's looking for known patterns of known viruses, and therefore it's very easy to circumvent. For targeted attacks, you just modify a virus. There is some degree of heuristic detection in antivirus where it will try to detect malicious behavior instead of a signature, but that detection tends to trigger on innocent software, so it's generally set to such a low level that it doesn't do much good. So server-side attacks find services your server might be offering and attack it. So if your server has got Microsoft file sharing turned on TCP port 445, which is notoriously vulnerable, there's often ways to exploit that and abuse the service to take over the box. That's how a lot of worms spread. The client-side attacks attack a client instead of a server, and typically they trick you into downloading something and running it, like a PDF file or an exe file or a script or something of that sort. So your web sites are running scripts all the time. Was Stuxnet a logic bomb? Well, I guess you could call it that. Yes, Stuxnet was a highly targeted attack which would infect machines and then try to reach certain Siemens controllers which were used to purify isotopes in Iran. And if it found anything else, it would just spread silently and wait to find the right target. So yeah, I think you could say it. I think professional military things are usually carefully targeted like that. I don't know if you'd exactly call a logic bomb, but it certainly seems to me like that describes part of its action pretty well. Most real malware includes features of many of these categories. Anyway, so if you use PHP, a very popular programming language, it has a fundamental flaw, which is why most people use PHP, their stuff gets hacked before long, which is that you very often have pages like this where you go to some page and then you have a parameter that includes the name of a page. So this is going to view that page or modify that page or something. And when this happens, you can often change this file name to something else. And this would be a remote file inclusion, where I send it to a URL that goes to some other page, which is now used instead, so I can add malware from a different site to the page. And then there's local file inclusion, where you just go to a local file, but that is one of the most common vulnerabilities of PHP, the way it's typically used. Java applets are not that common anymore, but they used to be pretty common, where you run a Java-based thing on a page, and then you have to run a local Java virtual machine. There are some examples that still use it. And so, and Microsoft's competing product was ActiveX, which I think is almost extinct now. Microsoft pushed it for years, but I think when they switched from Internet Explorer to Edge, it's gone. But it was the same thing. You would run compiled code in your browser. And it turned out to be very unsafe. It was very easy to write code that did malicious things. OWASP is the open organization of promoting web application security. There are representatives from every big company there, and many people would join it. The students in and I ran the OWASP booth years ago at RSA. Anyway, every few years they update this list of top 10 vulnerabilities, which is what everybody uses and all the vuln scanners and the companies and everything. So this is the latest list. Broken access control is where you don't really limit how people reach a page. There's some way to get to something without proving that you're authorized first. And of course, cryptographic failures are common, where you don't encrypt something at all, or you encrypt it with a bad method, or you leak the key out somewhere. Code injection, like SQL injection and cross-site scripting, is always one of the top ones. Then insecure design is where the logic of your business process makes it possible to abuse it somehow. And security misconfiguration is where some of the settings in some of your software is wrong, so it allows an insecure version of things. Outdated components, is the big issue of supply chain attacks these days, where you're using libraries and those are using libraries and some of those things are not up to date. And then identification and authentication failures, where you somehow do not really keep track of who somebody is sufficiently, so somebody without privileges ends up being able to do something where they should require different privileges. Software integrity failures are where people can modify software. This is what happened with the SolarWinds attack from Russia, where they modified the SolarWinds and everybody put this legitimate SolarWinds software on their machine, and they put on what appeared to be a legitimate update, but that update was poison that gave Russia control of their machines. And then failing to log and monitor is a relatively new entry in the top 10, but it's a very good point. You should be logging suspicious events and you should be monitoring for suspicious events, and that is a fairly new requirement for companies, but that's part of defense in depth and zero trust, where instead of having a perimeter and trusting everything inside the perimeter, you have to remain suspicious and scan and look for problems, because there are people who can sneak past your preventive defenses, and you have to detect when they're in your network doing bad things. And then server-side request forgery is this very strange thing added here, even though it's quite rare. This is a kind of attack where you trick a server into making an extra request of another server that comes from the server, which may be authorized to do something which you wouldn't be allowed to do from the client. Logging is tough without outsourcing? No, you do it all the time. That's why Splunk is incredibly popular. Splunk is the main tool for this. You put it on a Splunk server, and you forward the logs from all your devices to the Splunk server. And then you have a team examining those logs to see if bad things are happening. You do need a central logging location to get anywhere. Otherwise, it will just drive you mad. All right, and so there's service-oriented architecture. This is, I think, related to this thing they call serverless computing, where instead of focusing on one program running on one machine, you just provide a service. And so they're platform independent. You can put these in Azure and other cloud services. You can have a service where it listens and does some computation on data, but you don't even know what machine it's on or what operating system it's on. You only care about the service. Of course, it is on a server, but you can make it so you don't worry about that. The cloud provider worries about that. And then there's web services, typically sending data in XML or JSON or common ways to format data. Another one is SOAP or REST. These are just ways to structure data to send it to the server and get a response of some kind. Another thing you might use is WDSL. If you have multiple services provided by one box, you would have this WDSL where you can send a WDSL query and say, what services do you offer? And you would get a response. And that would be used to decide which services to use. Databases are where you store any large amount of data, like all your customer addresses, all your products, all your orders, all your credit card numbers, tax information, and things like that. And it turns out that securing this is difficult. And two types of attacks worth knowing about are inference attacks and aggregation attacks. And the controls are inference controls and polyinstantiation controls. So we'll get to those in a minute. Databases almost always have a primary key, which is one number which uniquely identifies every record. It could be a letter, but it's usually a number. And this is things like your social security number for federal systems, your city college student ID, Microsoft security identifier used to identify objects in the Windows operating system. You just have some kind of number that will uniquely identify objects, really records in your database. So even if two entries are similar in other ways, like you have two students that have the same name and the same birthday, you can still tell them apart because they have a different primary key. You almost always need this so you can keep track of what you're doing with databases. Polyinstantiation is where you have two rows with the same primary key, but they have different data for different clearance levels. So a top secret viewer will see all the data, but a person with only secret clearance will see only the data they're cleared for. That's one way to prevent some attacks we're going to talk about. So inference is where you can use low privilege access and you can gather the data and you can deduce the high privilege data. I mentioned this one, I think before, maybe in another class. This has been a trick known for a while. If you just watch how many people are ordering pizza at night, like how slow it is to get a pizza, that will tell you if there's a military operation being planned, because they'll make the staff stay late and they'll order pizza, and that'll use up all the pizzas. That's the sort of thing. A low security, observable thing is affected by high security activity. Aggregation is another way where you combine many low-level facts. For example, if you have a phone directory, like a Centrex, where the last 4 digits are all it varies, and you know some of those phones are classified, you could just take all the phones that are unclassified and see which ones are missing from the list and deduce that those are probably the classified ones. That's the sort of thing. Yeah, that's true. Good point. Pizza probably has a long wait in Washington tonight. Yes, they should be staying up late trying to figure out what to do from the Russian threat, which is a big deal right now. Anyway, so you can do things like this. One solution would be to make all your official pizza vendors sign a non-disclosure agreement so they won't tell anybody who's ordering pizza. Polyinstantiation is a control where you have a record of low privileges for every primary key, and there's a high privilege record, but you can't tell that by counting the low privilege. The presence of a low privilege record does not mean there is not also a high privilege record with the same primary key. That's Reezy. Yeah. So so let me go back. I can question. Oh, here's inference. All right, inference is where you take low-level access. You can infer the restricted information. Aggregation is where it takes many low-level facts. So inference is where you find a single measurable that leaks a secret. And aggregation is where you have to do data mining. You have to take a large amount of data to deduce the thing above it. They both essentially accomplish the same thing. It's just a question of how many facts you needed. All right. Yeah, that's the main thing. Anyway, so polyinstantiation is one control where you have the two kinds of data not separated by use of the primary key, so you can't tell that there's a missing primary key. And restricting the number of queries is an aggregation control where you just can't ask too many questions with low privilege within a period of time. You cannot ask enough questions to get a list of all the low privilege data to deduce what's above it. And so data mining is a related activity. Data mining is where you search a large database for useful things. This is, of course, what Google does, and it's what a lot of people do, and this is what a lot of open source intelligence does. So credit card companies do this. Alison Miller, who's very famous, I think she might be the head of ISC² now. She came and gave a guest lecture to my class a few years ago, and that was what she did. She was a mathematician specializing in game theory, and she got a job at the credit card companies solving this problem. You have customers out there making purchases, millions of them, and some of those purchases are fraud, and some are not. So you have to figure out how to decide when a purchase is suspicious. Does it come from China when there have been no other purchases from China? Does it have a funny amount? Is it buying a certain product that the fraudsters buy? That sort of thing. And turns out they're very good at that. Credit card companies can very well pick out the suspicious transactions and deny them. Data analytics is another way. This is all the rage since Snowden and Bradley Manning. People wonder, what if your own employees became disloyal and broke your security policies? How would you know? And so there are people who try to do data analytics to measure the traffic on your network and whatever else you can measure and decide if one of your employees is acting suspicious. All right, so countermeasures. To stop these sort of things, you can have multiple overlapping controls like administrative controls and then physical controls. This is what you have to deal with any of these systems where people might penetrate your defenses, and you want to have layers of defenses, so if they get through one defense, there's another defense that might stop them. Then there's mobile device attacks. Your people are carrying in cell phones and USB sticks and laptops and everything, and all those can be bringing in malware, so that's a problem. And so there are various defenses. You can just restrict policy, like you can't use your personal laptop for doing classified stuff, which I imagine is true. Isn't what basically Splunk? I'm not sure what you're referring to, M. Cath. Well, put something up there if you want to add more to that question. Anyway, then there's technical controls to stop people doing bad things with mobile devices. A lot of people restrict USB devices. You could restrict USB devices to only the official signed device your company gave you, which that's 802.1x authentication or other things like that. Various ways to identify trusted devices. And if you want to stop people from stealing things, you can back up the data. So if they steal the hardware, you won't lose your copy of the data. Splunk, yeah, Splunk can be used for network monitoring. There are other devices too, like intrusion detection systems and such. Splunk is technically log monitoring, but the logs can be of network traffic, and then it amounts to network monitoring. Yeah. All right. Other thing people do is they have full disk encryption and remote wipe, so that if somebody steals a laptop or an iPhone, they can't read the data because it's encrypted, and you have remote wipe, so you can remotely erase the device that's been stolen, and therefore hopefully protect the data on it. All right. So let's take a look at a Kahoot. I should have, here they are, 3E. This one. There we are. Yeah. All right. This is Unit 125. Good. All right. All right, I'll wait. Looks like people are still coming in. All right, maybe we got everybody now. All right, so what is it the FBI wants to add to the iPhones? They're always trying to do this. Yep, they want a backdoor. They want some way for the government to get the data off a phone and see if it's child pornography or some kind of criminal stuff. All right, what threat destroys a system on a certain date? All right, that's a logic bomb. Good. All right, so what language tends to have RFI phones? Yeah, that's PHP. All right. Good. Oh, and I see a note from a student who can't see the group chat. There is a group chat. It's on the right side. You might have to find a little arrow and click it to expand it. On Twitch, there is a group chat. Anyway, perhaps that's an old note. Anyway. All right. So, that's PHP. And who puts out the top 10 list of web vulnerabilities? Yep, that's OWASP. Good. And which attack searches a large database for useful data? All right, that's data mining. Good. All right. I know who that is. And I recorded that. Might be a real name or close enough to one for my grader. I'm not sure. All right. Good. Let's do a little more of these slides then. All right. So this is where we start cryptography. One of my favorite topics. Got a whole course in cryptography. Anyway, so we'll start with basic concepts. Cryptology is the science of cryptography. Cryptography is using it to make so-called secret writing where you can send a message and a normal person can't read it. It just looks like junk, but the intended recipient can decrypt it. And cryptanalysis is analyzing messages to find weaknesses and break into them. So a cipher is the algorithm. Plain text is an unencrypted readable message, and the point is you encrypt stuff and that turns it into ciphertext. And ciphertext is scrambled stuff that cannot be read by somebody that doesn't have the key. And you decrypt it with the key to get back into plain text. So your main thing you get out of cryptography is confidentiality. That's the main point, so that the eavesdroppers cannot read the contents of the message. You also tend to get integrity. It tends to be that the eavesdropper could not alter the message, and if they did, it would not decrypt. But that's not the primary purpose of most cryptography. The main primary purpose is usually confidentiality. Although you can have message authentication codes which use cryptography just to produce integrity, to put a signature on a message so you can tell that it has not been altered. All right, authentication is another thing you get from message integrity codes, where you have a signature that identifies who created this message or who sent it. And then there's non-repudiation. You can put signatures on records so they can't be altered, and then people cannot deny what they've done. So if you get money from the bank and you mortgage your home, you cannot deny later when you fail to make the payments and they want to take your house from you. You have the bank will say, we have a non-repudiation proof that you really took this money and agreed to pay your mortgage. That's what you need for most legal agreements, is sign something that you cannot deny later that you did it. Confusion is the property that there is no relationship between the plain text and the ciphertext. So changing one letter of the plain text will change a lot of letters scrambled all over the ciphertext. So you will not find a pattern in the ciphertext that's directly related to patterns in the input. Diffusion is a similar thing. Plain text should be distributed throughout all the ciphertext. These are desirable properties of a good cryptographic system. Substitution is where you substitute one character with another, and that provides confusion. So you could just change each letter to a different letter, and now the ciphertext will not have a connection to the plain text, but it will have patterns, because changing one letter will only change one letter in the output. So permutation is where you rearrange letters to provide diffusion. These are common operations to scramble things. So you can define how good a cryptographic system is by its strength. A strong encryption means that nobody can decrypt it, even if they know the algorithm, even if they have a powerful computer, without the key. And you rate them by the work factor, which is how long or how many cycles it would take to crack it And so secrecy is not considered a good defense. This is a common mistake people make. They think I'll make a system and keep it secret, and that usually doesn't work. That doesn't really protect it very well because there really aren't that many different things you could do. And usually when people keep it secret, it's because they didn't really use a standard strong system. Most commercial products that won't tell you what they're doing are usually doing something stupid and wrong. That's why the general rule is you should use an open system and you should just tell people what you're using, and it should be a good system like AES, the standard one, which you know is very strong. Now the military uses secrecy and a strong algorithm as much as they can, but in the non-military world, you definitely just want somebody to tell you they're using a standard algorithm that you know is strong. So monoalphabetic ciphers are where you change, these are for the old ciphers before the modern things like AES, but the principles remain the same for later ciphers, where you change one letter to a different letter. And if you have another recurrence of the same input letter, you have the same output letter. So this can be broken by frequency analysis because the letters are not equally likely to occur in English. E is by far the most popular letter, so if you have a few paragraphs of ciphertext, you can just find the most popular letter, and that's probably E. And you can continue to use similar frequency analysis to deduce a lot about the message and figure out the key. Polyalphabetic ciphers prevent this by using a system where if the same letter occurs again, it will be changed into a different letter the second time, a different letter the third time, and so on. That will prevent frequency analysis, or at least make it less efficient. Modular arithmetic is a necessary feature. If I have data that's a series of bytes, I want to encrypt it and get a series of bytes. And usually I don't want the ciphertext to be different in size to any great extent from the input, so I want to just use modular arithmetic where I can go around, there's a certain number of possible values, and when I scramble it, the end result is still going to be in the same set of values. So here's the example of a clock face. If you put 0 for 12, this is a mod 12 system. If you're at 11 o'clock and you wait 2 more hours, you're back to 1 o'clock. If you're at 2 o'clock and you want to go 3 hours ago, you're back to 11 o'clock. You never go outside these numbers. Even if you keep adding and adding, it just go around and around this ring. This is how cryptography works. It works on a ring, scrambling data, but within a limited set of values. Then another thing you use is exclusive OR, an essential part of almost all cryptographic systems. This is how you combine one bit of data with one bit of key, one bit of plain text with a bit of key. So if the plain text is 0 and the key is 0, you get 0. And the rule is if the 2 bits here are the same, the answer is 0. If the 2 bits here are different, the answer is 1. So 0 and 1, or 1 and 0 give you 1. 1 and 1 and 0, 0 gives you 0. That's called exclusive OR, and it's used by AES and many, many cryptographic systems. And one thing about XOR is if you XOR something like here's attack at dawn, and I'm going to scramble it, XOR it with this key, which is apple, apple, apple. And so it turns into this junk, dollar signs and dashes. But if you XOR it again with apple, 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 it goes back to the original state. XOR undoes itself because another way to look at XOR is every place where there's a 1 in the key, you flip the bit. So this 1 makes that 0 change to a 1, and this 1 makes that 1 change to a 0. But where there's a 0, you don't flip the bit. So if you XOR it again, you'll just flip those same bits back to their original state. That's why XOR reverses itself. That is a known property of it. You do not need to write an XOR encryptor and an XOR decryptor. They're both the same. Yep, XOR is simple. All right. And XOR alone, by the way, is of course not a strong cryptographic system, but it's part of a cryptographic system combined with substitution and permutation and so on. You get a strong system like AES. So encrypting data at rest is what you use like BitLocker to encrypt your hard drive when the computer is turned off. That's encrypting data at rest while it's stored. And the only point of that is if somebody steals the whole physical device, they won't be able to read the data. Encrypting data in motion is data while it is being sent over a network. That's what we typically want here is end-to-end encryption like HTTPS, where there's a key only at the server and not at intermediate places. So nobody can read it except the intended destination. And that's what VPNs provide also. You're encrypted to your VPN provider. All right. So when you're choosing an encryption method, you have to consider how fast it is, see if it's going to slow down your data, how strong it is, cost and complexity, and other considerations. All right. And let's take a look at another Kahoot, which is 3F. Looks like it's this one. All right, I guess that's it. All right, so a video shows Marjorie at a meeting and she can't deny it. So what have you got there? As we were talking in the news, Marjorie Green went to a meeting and then later on probably wanted to say she hadn't been at that meeting. Yep, that's non-repudiation. All right. All right, Caesar moves each letter 3 steps in the alphabet. So what have you got there? That's substitution. Your A turns into a D, and if you have another A, it also turns into a D. Each letter is just replaced by another letter. That's a substitution cipher. All right, which system resists frequency analysis? All right, that's polyalphabetic systems. All right, so what's 17 mod 5? It's 2. What you do is you divide by the modulus and keep the remainder. So 17 is 3 5s, or 15, and 2 more. So it's 2. That's how it works. All right. And what is the number 3 XORed with the number 4? Not the ASCII character, but the number. All right, and the answer is 7, and let me just bring this up because this one here usually inspires some suffering. So let's go through this one. All right, so 3 is 1 1 in binary, and 4 is 1 0 1. So if you XOR, well, 4 is 1 0 0, pardon me, there we go. So if you XOR them, you get this is 0 and 1. And so this bit is 1. This one here is what I wanted to do there. And the next one is 1 and 0, so it's 1, and that bit is 1. That's how you do it. You do it bit by bit. And this is 7. 1s, 2s, and 4s. So 3 XOR 4 is 7. Anyway, that's how it works with good old XOR. All right. All right. Let's make this smaller again. Shannon is 1 twice, and Greg is 1 twice. All right, and Pal is a new name. I hope that's a good enough name for my grader to find you. All right. All right. So, I'm going to stop this video.